computer. There we go. Hello, everybody. Welcome to the Montana Tech Public Lecture Series. And this is our Earth Science and Engineering PhD program speaker as well, and as well as our Chemistry and Geochemistry seminar series speaker. This is recorded today, and the recording will be posted. I do have everybody muted on entry, so we shouldn't have any problems with people popping in with noise coming in. And then Des will talk for about 50 minutes and then answer some questions there. And then we have a little small chat discussion room for after the talk. If you're interested in joining that, you can go ahead and email me and I can send you the link right after the talk. So with that, I'd like to introduce Dr. Desiree Plata. And Des earned her bachelor's degree in chem from Union College and her PhD in chemical chromatography and environmental chemistry from MIT and the Woods Hole Oceanographic Institution. So Des was part of my program. Des is a NSF Career Awardee and all sorts of other awards as well. So Odebrecht Brascom Sustainable Innovation Awardee, National Academy of Engineers Frontiers of Engineering Fellowship, two-time National Academy of Sciences Kavli Frontiers of Science Fellow, Caltech Resnick Sustainability Fellow. She is the Gilbert W. Winslow Career Development Associate Professor of Civil and Environmental Engineering at MIT, and we are very pleased that she could spend this hour with us as well as a little bit of discussion afterwards. So Des, thank you very much for coming to speak with us today.
Yeah, it's a real pleasure to be speaking with you. I wish I was there in person. I have a family out in Butte and Livingston area, and it would be great to be with you. But I'm happy to be joining you virtually to talk about what is really a very complicated problem, and hopefully I'll get across that it's not as simple solution as waving a magic wand like you often hear about in the media. And it's really, I don't consider the fossil energy issue a partisan problem or something that really even has two sides. It's a very multifaceted problem, and I think that you'll hopefully see by the end of the talk that there are a lot of different angles that need to be addressed in order for us to make a transition into a more environmentally and economically sustainable future. So there's been massive growth in solar in the last 10 years, and the types of images that you see here, this is a real photograph. This was just fantasy when Alicia and I were in graduate school in the mid 2000s, but this has been installed at large scales. And what I'm showing you here are these drastic changes in US electricity generation over the last several decades. And so what I want to draw your attention to is right before the 2010 timeframe. A few things that you're going to notice is a dip. The dip is the economic recession. We can measure recessions in energy consumption. There will be one for the coronavirus pandemic shutdown. I'm going to show you that data momentarily. But a few things that you notice here is that the growth that you see in renewables, that green bar, is actually quite small. And the growth that you see in the blue bar is actually quite large. So there's an explosion in natural gas extraction, as many of you probably know, since about 2008. And we anticipate that looking into the future, natural gas is going to continue to supply a critical fraction of our electricity in the United States. So there will be growth in the renewables. You see the total wedge continues to grow. That's because the population grows and our GDP and quality of life we anticipate are going to continue to grow, even though it doesn't seem like it in 2020. But natural gas will kind of always be there as an important fossil fuel to meet our needs. Coal is anticipated to shrink quite a bit, as is probably no surprise to many of you. This is today. So I just pulled this off the Energy Information Administration's website about 2 minutes ago. And these are the updated projections that incorporate changes in response to the coronavirus pandemic and things of that nature. So again, you see the dip in natural gas production, crude oil production. There's a dip in total energy consumption, but overall, we anticipate that we'll see a continued growth in these sectors. Now, One of the things that one of the reasons that you continue to see growth in fossil energy extraction, even though there's a lot in the media about why we need to switch to totally renewable energy sources, is because solar and wind intermittency is real. We're actually very good at getting the sun's energy and the wind's energy into the electricity grid. We're okay at storing it. We're pretty bad at distributing it when we need to. And so this is not a very sophisticated diagram. I'm going to walk you through it. But basically, what you see along the bottom of the plot is the time of day. And what this says is that the sun comes out during the daytime. So after about 6 a.m., the sun is up, and then the sun goes down at the end of the day. And grid demand, how much electricity people want, that's shown in the red line. That actually doesn't display the same pattern, which makes a lot of good sense because we don't need the lights on as much when the sun is out. And so the grid demand is high in the morning when people are mobilizing to get to work, and it's high in the evening when people come home and start doing laundry and things of that nature. Wind supply is kind of always there and is more weather dependent, and that's shown in the black line. So the crux of the problem here is that the sun is out when we don't really need it. And so we need to figure out how to get that solar energy to be distributed when and where we need it. And that has to happen really quickly. And so what you're looking at here are different curves that represent different years. And the something a phenomenon that is demonstrated by this is something called over generation, and this means that you're generating so much solar electricity that you risk burning out your grid. And this is actually a reality that California is facing. So as the years go forward, as you go down those lines, they get more and more electricity in the day, and then the ramp up is what they need at the end of the day. So when people are coming home and trying to do their cookwork or cooking and the house chores and things like that, you need a lot of energy really, really fast. And fossil fuels are one of the only things that can do that. There are also some, economic constraints here. Fossil fuel power plants are only economically viable when they're running all the time. And so there has to be some kind of baseline supplied to the grid, and that adds complexity to this. But this curve is known as the duckbill curve. And the duckbill curve is really very representative of the problem that we face. As I mentioned a moment ago, California was generating so much electricity and had to deal with this overpotential risk that they actually paid the state of Arizona to take electricity from them in just 2017, which is kind of mind-boggling, right? And so we're so good at getting solar energy that we have to sell it to other people so that we don't blast apart our grid. And so a lot of the challenges in renewable fuels are associated with what's called optimizing the grid's demand. And those are really computer science problems. We think we have the material science problems solved around this. So there are some other things that you also can't electrify. So this notion that we can use renewable fuels and batteries for everything just doesn't hold true. And in particular, there are a few sectors that I want to highlight on this figure. You're looking at the state of Massachusetts's greenhouse gas emission budget. And one of the things that you'll notice, first of all, is that between 2005 and 2012 or so, there's a dramatic drop in the total greenhouse gas emissions. That's actually almost wholly associated with the switch to natural gas, because you can get more energy for fewer greenhouse gas emissions with a simple switch to natural gas. And lots of global economies have actually experienced this same drop in greenhouse gas emissions because of natural gas and natural gas energy extraction. But a few of the wedges that really aren't impacted by this that you're going to notice are, I want to point to the purple one, that's heavy duty vehicles. So these are long haul trucks. I also want to point to residential and commercial at the bottom. That's really, you can think of that as home heating in many ways. So just because renewables are available doesn't mean that everyone can heat their home with wind and sun electricity. Many people's homes are in the New England area, especially, are heated with traditional carbon-based fuels. So even if you're burning a wood stove, that's a carbon-based fuel. Aviation is another one that's really tricky. So that's the orange bar that appears in the middle of the plot. And aviation is very difficult to decarbonize, so to speak. So in order to get a passenger jet into the sky, you have got to use carbon-based fuels. So there are a few sectors that are really difficult to decarbonize, and this is the reason that fossil fuels are necessary. For those students who are in the audience, this is a major challenge that that is facing you technologically. So which fossil energy are we going to use? Well, you can probably imagine that I'm here to talk to you today about natural gas extraction. So I'll focus on that, even though there are other energy sources. And the reason that we favor natural gas for this so-called transition to a renewable future is because you can emit less CO2 per unit energy. And I'm showing kilograms of CO2 per megajoule of energy here. And liquid natural gas is that tiny little bar on the right-hand side. So compared to other fossil energy sources, liquid natural gas actually does really well by the greenhouse gas metric. Now, there's some question about how tall that bar should be if you account for fugitive emissions of methane, which is another type of greenhouse gas. And we'll talk about that in a little while. But in general, natural gas produces much less CO2 per unit energy than the others. And so this downturn that I talked about in greenhouse gas emissions is due almost solely to that switch to natural gas. It's not like we've innovated lots of new technologies between 2005 and 2020. We've got lots of new social media apps, but we haven't done very much in terms of tough tech, and we could be doing better there. But our progress towards those diamonds that are showing up in the middle of the plot is mostly due to natural gas, turning the switch to natural gas. And those are targets, by the way, to Paris climate reductions goals. The other reason that we like natural gas is because it's really energy dense. So again, if you look all the way to the right-hand side, you'll see liquid natural gas, and it's got a lot of energy, a lot of megajoules per unit mass and per volume or per liter. And so that helps us when we need to move fuels to locations where we need it. So you can think about moving city buses around. That can be done with liquefied natural gas. So it's lots of energy per unit mass, which is a good. The other great thing that we love about natural gas is that it's trapped in shale rock. I haven't spent enough time in Montana to know if you have shale outcrops like this, but this is one from the state of Pennsylvania. And there's actually so much natural gas in these shale formations that you can light a match and operate that natural source like an eternal flame. So shale rock, this is a picture of an outcrop here, but it's typically buried around a mile beneath the Earth's surface in upstate New York and Pennsylvania, and as an example. And that depends on where you are in the world, but typically very deep beneath the Earth's surface. And so here's an image of several different shale, so-called shale plays around the United States. And we have a lot of natural gas in the United States. And so this we see as a really good thing. You know, in 2005 and 2008, we were embroiled in a couple of different wars centered around the availability of fuel resources. And so if we, making this switch to a domestic fuel source allowed us to disengage and stop literally fueling with our dollars those conflicts and provide our own sufficient resources at home. And actually, the U.S. has become a net energy exporter because of this. So if you look at the blue dots here, those are natural gas production and consumption. But consumption is the solid markers there, and the production is the open markers. And we're also concurrently producing crude oil, actually, when we extract this gas and bring it to the surface of the Earth. There's a picture of a flame that's you can roast your hot dog on if you ever make it to Cook Forest, Pennsylvania. And so the U.S. has become an exporter of petroleum and a net exporter of liquefied natural gas, which is not the history. So for those of you who remember, you know, the U.S. in the 70s and even just 20 years ago, we've been a net importer, and that's no longer true. So the reason I'm mentioning all these wonderful things about natural gas is that it's functionally an inevitability. So we need at least some fossil fuel. We have a great source in natural gas because it's domestic, it's abundant, and it meets our needs. It has a lot of energy per unit mass or volume, and it has lower CO2 emissions than what we are used to dealing with. Excuse me a second. I'm hoping you can hear me. I see there's a chat. I just want to make sure. Oh, okay. I don't know. Sorry, Larry, I'm not going to address this. Just want to make sure the audio is coming through, but I'll hopefully can do that at the end. So today I'm going to talk about horizontal drilling with hydraulic fracturing, because in spite of the benefits that we get from fossil energy extraction, there might be some concern for environmental impact. So the image that you're seeing here is a natural gas drilling well pad, and this well pad is containing the tailing and other fuels that have come back to the surface, other liquid products that have come back to the surface of the earth. So let me just try and get, sorry about that. I use an app that doesn't cooperate with Zoom very well. So there we go. So the very basic idea around fracking is that you have to drill a hole in the ground. That hole is typically just a plain well bore that has steel casing down through an impervious rock layer and concrete casing that goes below the groundwater layer. Once you get to that lower layer, you can, the novel part here really in the last 15 or 20 years is that you can start to make those drill bits make a right angle turn functionally. It's a more gradual than that in reality, but what that means is that you can access a lot more space from a single well. So instead of having a single borehole, you can actually access lots of horizontal area within the shale formation from a single hole in the ground. So we can really be much more efficient with our gas extraction process. And there's a few different types of fluid that I'm going to talk about. One is frac water. That's the mixture of water and chemicals that are injected into the ground. And the other fluid that I'm going to talk about is flowback water and produced water. So after you have created this high pressure event that fracks open the rock and allows you to extract the natural gas back to the surface, you release the pressure, and that allows fluid to come back as either flowback water early in the fracturing process or produced water late in the fracturing process. And some questions arose early on in this work as to whether or not there was going to be a path for this water to make it into the groundwater through that impervious layer. Are we going to be causing seismic events off axis where buildings aren't up to code? And what are we going to do with the treated water or with the wastewater that comes back to the surface? Do we treat it? Do we truck it away? Or a combination of both? This process tends to be fairly water consumptive. So you can see some of the early impoundment dams in the image in the foreground that are very close to people's homes. And you can see the number of tractor trailers that have to come on site. And people actually complain quite a bit about the truck traffic in these cases. And those trucks are often bringing chemicals and water to initiate the frac. So the types of chemicals that are in flowback water really span a very wide range of chemical characteristics. Some are solids at room temperature, some are liquids, and some are gases, of course. So examples of things that are solids at room temperature are things like salts and things like uranium. Those are there as a result of natural processes. Gasoline is a representation that I'm showing here of the types of liquid at room temperature chemicals you might expect. So gasoline-like or diesel-like compounds coming to the surface of the earth, and then methane. And those are again, all naturally occurring materials that are being extracted to the surface, along with a combination of what's being injected along with the frac water. My expertise is really very focused on the carbon-based end of this. So looking at compounds that are like the diesel hydrocarbons, the gasoline-like compounds, and methane. And so we tend to work in what's called a gas chromatography amenable region of this figure. The figure I'm showing you here, you can think of as a measure of hydrophilicity versus hydrophobicity on that bottom axis, that x-axis, against molecular weight on the y-axis. And every little dot on this figure is a different compound that's been disclosed for use in hydraulic fracturing. And these tend to separate on the basis of how you analyze them in our world. So do you analyze them with something called gas chromatography or liquid chromatography? And gas chromatography is really good for hydrophobic compounds that occur on the right-hand side, on the lower right of this figure. So I'm going to spend my time focusing in that gas chromatography amenable region because that's where the products are. So I often will tell my students, if you want to um, get anywhere with environmental problems that involve industry, you had better be sure that you're also focusing on the bottom line or the product so that you can offer improvements in technology along with better environmental benefits. And so here are a few of my students working in the lab to extract some of these so-called flowback water samples. And there's basically on the right-hand side, you see that we can do many of these at the same time. The central image shows real flowback waters being extracted into hydrophobic solvent. So again, we're looking at really hydrophobic chemicals, and this process allows us to get them out of the water and into a method that we can look at. And this is just our group having some fun in the summer. So actually a lot of work that took about the work I'm going to tell you about now took about 4 years for us here. So because it's a complex mixture, we need to have some understanding of all of the different compounds that are there. And we do that with a process called gas chromatography, which I've mentioned. And this basically takes a liquid sample, turns it into a gas, and then takes all of those many hundreds and sometimes thousands of molecules and allows them to interact with in a column. And so the column, or the orange piece of the circle that you see on the left-hand side, is can be up to 60 or 110 meters long in some cases. And as the compounds are traveling along that column, they separate. And in many cases, we do something called one-dimensional gas chromatography, but in this case, we're going to use 2 dimensions of gas chromatography. So we're going to freeze out everything that comes out of the end of that column and re-inject it onto a second column where we separate on the basis of an orthogonal property. So in this case, we're separating on the basis of volatility and polarity. And so what that does is it takes a sample where you might have had co-eluting compounds. So the blue curve, the red curve, and the green curve might have all come out together before, but now you chop it into bits and re-inject it onto that secondary column and start to separate that blue feature, the red feature, and the green feature. And then you can reconstruct that mathematically and look at it from the top down, very much like you would look at a topographic map, where each one of those little peaks is now representing an individually resolved compound. And so this was a really important revolution for oil and gas work, because what you took a sample that might look like this, an unresolved complex mixture, and turned it into something that looked like this, where you could actually see an individual feature as opposed to one big hump of material coming out, where you've got maybe dozens of co-eluting compounds. So again, we have a volatility separation on the bottom axis here and a polarity-based separation on the y-axis. And where the heat map here, where the red features are the tallest ones, letting us know where there are compounds. So just a little chemistry refresher, because I'm going to tell you a bit about what we found in that complex mixture. I think most of the audience probably is aware that the C's and the H's are carbon and hydrogen. The lines between them represent bonds. And for organic chemists or people who are thinking about taking organic chemistry, carbon always likes to take 4 bonds. So that means there should be 4 lines connected to it. And so organic chemists developed a shorthand where they actually said, I'm sick of drawing the hydrogen, so I'm going to leave those off. And they generated the structure on the right, that little hexagon. And that when we see a corner in that hexagon, we know there's a carbon atom there. And if the carbon doesn't have 3 lines coming out of it, we know there has to be a hydrogen there too. So that's the cartoon representation that we're going to use. So carbon takes 4 bonds. And here's some of what we found. So we had about 2,500 different detections in this. This is just one sample of flowback water. And after about 4 years, we were able to identify a little more than 700 different compounds. And so that sounds like a lot of material, but I'll walk you through this. And one of the things that we found was kind of a unique presence of geogenic compounds. So we expect oil, everything in that yellow region, to be there. That's very classic oil signature, but we don't really expect everything in the upper left-hand corner. Those more polar compounds are actually quite rare to see in an extracted oil sample. And so we dug into this to ask ourselves, what is there? And one of the things, and how common is it? So in 6 different flowback water samples, what you can see is that no two of them are alike. So there's this wild heterogeneity among the samples. But that oil mass that's kind of in the central bottom of the figure, that was dominant, that was present in lots of places. Those unique structures were there sometimes. And then we also identified lots of different phthalates. Phthalates are plasticizer chemicals that are abundantly used in industry. And so it's not very surprising to see those. One thing that you can't see on this, but I want to point out, are halogenated substances. So halogens are things like chloride and bromide and iodide. You've heard of them before, but they tend to be thought of as non-reactive in these salty environments. But we were finding them as additives on all of these organic structures. So they weren't disclosed for use. So we were wondering what they were doing there. So just as a recap, we saw these phthalates, which kind of stood out as being industrially impacted, halogenated compounds, and there are a few other interesting features here that I'm not going to walk through in the interest of time. But I want to point out that those halogenated compounds, when you add chlorine and iodine and bromine to organic structures, they can sometimes have enhanced bioactivity, and so we were particularly concerned about those. So when this is my advice to the budding geochemists in the rooms, is that you should never aspire to be a finger pointer. If you identify a problem, the very next thing that you should do is identify the solution. And that is, I think, a more rapid way towards progress. The first part is important, but you've got to stick with it to identify the solution, or the second part. And so one of the things that we set out to do, or we asked ourselves, was, is it possible that these compounds are really forming in the subsurface? And if they are, what can we tell industry about how to change their operation practice to perhaps avoid the production of those enhanced or more toxic chemicals? Now, one of the things that was troubling us in this work is that we had to simulate a high pressure, high salt, elevated temperature system, and those reactors tend to cost on the order of $20,000 a pop, and graduate students are even more expensive. And so I didn't want my grad students sitting around doing one experiment over a really long time period. So I asked him to design something that would give us a higher throughput reaction, and he came up with this. And I won't walk you through all its really cool features, but it basically allows us to do 15 different experiments all at the same time. And if we're really careful about how we turn this over, we can do chemical sweeps, or we can do kinetic time series. And this really dramatically enhanced the rate of discovery from one chemical per PhD student, which is about 5 years, to dozens of chemicals within that same time frame. It still isn't very much, but it's a big major step forward. And we were able to build this entire device for around $5,000. So it uses rare earth magnets to get mixing in high pressure vessels. Those there's some sous vide heater from Amazon on that, so low cost heating. And those styrofoam balls that you see in the top central image are actually helping fight evaporation. And we've got like an automatic fish tank leveler in there, so it's a pretty low budget way to do a lot of experiments quickly. And using that clever system, what my student was able to show was that there is evidence that these salt-derived chloride, bromide, and iodine species are actually adding to organic chemicals that are present either in the formation or as additives themselves. Now that's pretty atypical to think of salt as being reactive, and so we had to figure out what was going on here. And it turns out that there is an additive in the process called persulfate that's there for an important functional reason, but it's activated at higher temperatures, and that persulfate became reactive at higher temperatures and started to form these reactive halogen species. And this chemistry is actually very similar to something that happens in wastewater disinfection. And so it wasn't entirely unknown. It was just unknown that it could happen in a natural or industrial natural hybrid setting like you get in hydraulic fracturing. And so the things that we discovered were that, temperature was really important to this process. The salt composition was also important, as you might imagine. And the chemical additives that one chooses in the area were also critically important in this formation process. And so we asked ourselves, if we can if we can identify those rules, perhaps we can give advice to operators to try and avoid that unwanted transformation chemistry, or municipalities who might be interested in testing for it, or wastewater engineers who might want to specifically target the treatment of those chemicals. And one of the reasons that we think prediction is so important is because there's just under 700,000 hydraulic fracturing wells in the United States, and only about a little more than 200 of them have been measured for these types of organic chemicals. Clearly, it isn't practical with respect to time or money to go out and do a comprehensive analysis. Remember, I told you it took us 4 years to figure out what was in those stinking 6 flowback samples. And so computers can really help us here to close this gap. It turns out that we know from the US Geological Survey quite well what the bromide concentrations, the pH, are in these shale formations, and we can know quite well what the temperatures and pressures are in those same formations. And so bringing together all of this data and applying some of our rules about transformation chemistry, we were able to ask the question, well, if we have a well right here, and we know the geochemical conditions of that well, and we happen to know what chemicals an operator is using in that region, can we predict what types of chemicals we would expect to see in the flowback water and potentially create a flag to try and avoid the formation of those compounds? And so, one of the ways you might use this tool is to prioritize regions of high risk. So the way that you read this map is all the gray dots are anywhere where there's a particularly susceptible organic chemical in use. The darker gray dots are anywhere where that activator compound, that persulfate, was added. And the blue and red dots show increasing well criteria where you would definitely expect this type of chemistry to happen. And so pretty soon you start to reduce the vast experimental space down to a few important shale basins where you could say, okay, operators, maybe in this region we want to use something else to perform that critical function that the persulfate usually serves, as opposed to using it in this case where we might anticipate seeing toxic products or products that are going to actually sour your gas. So another way that you might use this is to leverage our understanding about what happens in wastewater transformation systems and surface water chemical transformations, and actually predict the concentration of the compounds that you would expect in a region. And so we can do this for different basins and start to say, what do we expect the concentration of these types of halogenated compounds to be there? Just to define an acronym here, that red line is marking the Safe Drinking Water Act maximum contaminant level. That's what MCL stands for trihalomethanes, and that was the example class of molecules that we were using here. And what you can see is that most of the water samples are going to be just fine, but the ones that show up to the right of that red line are the ones where you're going to need to focus in and be concerned about. So after doing that, we had asked ourselves, well, is there actually evidence for these compounds showing up in drinking water in homes? So all the work I just told you about was about flowback water. That was industrial wastewater. Really, nobody's drinking that. So we wanted to see, is there any evidence that we have impacts at drinking water wells in people's homes? These two things that I'm going to talk about, GRO and DRO, are gasoline range and diesel range compounds. And if I know some Montanians, I expect that you are aware that gasoline range compounds are lighter, diesel range compounds are heavier and contain more energy. And so that's there are two classes of compounds. And one of the things that we saw here was that gasoline range organic compounds were not showing up first in drinking waters. And diesel range organic compounds, the heavier, stickier ones, were. And that didn't make any sense from a groundwater transport perspective. And so there had to be another explanation for what was bringing those heavier compounds into groundwaters. We knew that it wasn't from leaky well casing because there was no evidence that the methane was showing up along with those diesel range compounds. That's the figure you see all the way on the left. We knew that the water that had diesel-like compounds in it was geochemically young. That means it was coming from the surface potentially and not depth or from underneath. Because if it did, it would be enriched in an isotope called helium-4 that comes from the naturally occurring radioactive decay processes. And we didn't see that. So we knew that it's not coming from leaky casing, it's not coming from depth. But one of the things that we did see was some salt associated with the groundwater with high diesel range signature. And so if we take all of those things together, we know that we don't have leaky casing. We don't think this is coming from leaky we know that and that really left surface spill disclosure databases and violation reporting databases to figure out how common are chemical spills. And it turns out that they're remarkably common, but it's very hard to know if they are occurring in large volumes or what types of chemicals, because that is not very well documented. But the good thing about the potential source of a surface spill is that we can know when homeowners to use point of use water treatment filters. If there's a contaminant there and we know what that contaminant is, we can insist on better engineering controls, or we could have a faster response. And so that is all very encouraging. There was also no evidence in our study that there was long range transport of organic compounds. In other words, things that had been there naturally over long time scales don't show up in the groundwater. Things that were injected aren't showing up in the groundwater either over these things. So we did this study again about 10 years later to see, well, maybe we were just looking too early. Maybe this is a process that's slow. And so we went back and sampled many more homes, almost 10 times as many homes. It was a real tour de force, and we're just wrapping that up. We went out on our last sampling trips this past fall, and all of that water is actually quite clean as well. So there isn't a lot of evidence of these diesel-like compounds or spectrum showing up in people's drinking water. The transport times for those chemicals through groundwater systems. Now, this figure that I'm showing is a little bit difficult to interpret, so I'll try and walk you through it. What I'm showing on the x-axis, the bottom axis, is time for over a decade, and distance is shown in kilometers on the y-axis. Now, the blue circles are showing you how old all of the nearest wells are and how far they are to the nearest home. So they're all within a kilometer or two. Actually, it's very hard to find a home in this part of Pennsylvania that has a well more than 5 kilometers away. We actually have to go to New York State to find control wells. And so within that range of distances to the nearest well and ages of the gas wells, what we might look for is an overlap of the red and the gray bands. And those are really representing transport time scales for something like a phthalate, that's the gray band on the bottom, and something that's faster moving, the red acrylamide curve. So even in really extreme cases, so the full width of the band, you don't see a lot of overlap with that fast moving acrylamide and the well. So in other words, it just takes too long for acrylamide or bis-2-ethylhexyl phthalate or these organic chemicals to get to the wells. And they tend to be degraded before that happens. Another way to look at this is to think about the well's catchment area. So these rainbow colored blobs are representing the probability of catching something that's been spilled on the surface. And what you can see is that there's a wider catchment in panel B, the top panel, that's for the acrylamide, a more narrow catchment for C. So if phthalate's going to show up in someone's drinking water, it really needs to be spilled very close to their well at the surface. And this is one of the reasons that you don't see a lot of organic chemical contamination associated with hydraulic fracturing, because the transport timescales are very long, and the geology, at least in this region of the country, is actually quite protective of the homeowners. And this is just another way to think about that capture probability. So what's everybody worried about with hydraulic fracturing? Well, after I can tell you about a couple of the other types of contaminants. I didn't talk about the salts and the radioactive materials in the Q&A session, but I want to make sure we leave time for that. And one of the big concerns that people have about natural gas extraction, excuse me, is that methane is a very mobile molecule. I don't know if you can hear the audio on that file. So it's a light gas. It moves around really efficiently, and atoms really dance around quite a bit. And so that vibrational, those so-called vibrational modes of methane absorb heat. And so methane is a very potent greenhouse gas. And you can see that methane leaks out of these natural gas facilities. And this is an image from National Public Radio showing North Dakota sky at night lit up as if it were a big city, which it's not, of course. These lights are from presumably natural gas flares. And so this is where natural gas or methane is leaking out of the ground and has been lit on fire to convert it to CO2, a less potent greenhouse gas. But it's estimated that these losses represent maybe up to 10% of production volumes in some cases. And so we worry about those methane losses. Methane is controls or mitigation of methane in the atmosphere is remarkably important to limit the total impact of climate change, so the total temperature rise. So this figure that I'm showing you here are historic temperature records in the black, and a couple of different cases or what ifs. So the reference case, if we do nothing, shown in the purple line, the red curve showing us what would happen if we just had CO2 controls, the blue if we just had methane and black carbon or BC controls, and that bottom line showing if you have CO2, methane, and black carbon measures. And the take-home message here is that in order to keep yourself under a 2-degree temperature change, you really need to have some kind of methane control. And so we can't just be poking holes in the surface everywhere and allowing methane to escape. The other reason that methane is so critical is that it does its damage in the near term. So this figure is something that many students in the audience have probably seen. It's showing gigatons of CO2 equivalents on a 100-year global warming potential over time since the 1990s. And I'm showing in green and nitrous oxide, that's the laughing gas that Dennis gives you, in gray. And when you look with the 100-year global warming potential, methane only does about 16% of the damage. But if you actually look at the 20-year time horizon, so what's going to happen in the next 20 years of our lifetimes, you see that methane does as much damage as CO2. That's kind of I like to call it the elephant in the atmosphere. It's the greenhouse gas that everybody should be talking about, but nobody really knows about. And so on the 20-year time horizon, methane, it does 86 times as much damage as CO2 does on a per mass basis. And so it's something that we should start paying attention to. And we haven't been going in the right direction with respect to our methane emissions. The observations shown in black are actually tracking with the worst case warming scenarios. And that's not true for CO2. We've actually done a good job turning CO2 over. And this year there's going to be a big dip in CO2, and that will presumably rebound when people start moving around the surface of the Earth. So one of the things that we've been thinking about is how natural processes actually degrade methane in the atmosphere or in sediments. And I'm showing a cartoon of a protein structure on the left-hand side of your screen called methane monooxygenase that's able to bind and convert methane. And so we've been thinking about how you get a methane monooxygenase like chemical functionality in a porous material. I'm showing an aerogel that has a high surface area on the right-hand side, and as an example of one type of material that we might be able to use. So here's an example of where we tried to capture the chemical functionality of the active site in methane monooxygenase and shove it in an aerogel that has a lot of surface area to interact with the gas. We've been using these materials to try and convert methane at atmospheric levels, so very trace component of the atmosphere, into not methane. And it really doesn't matter very much what else it is, as long as it's not toxic and it's not methane, it's good for the atmosphere. And so some scientists have proposed that we could install big fans to try and increase the interaction of gases and the atmosphere with these types of catalysts, or paint buildings with these catalysts. So on the right-hand side, I'm showing a parking deck in Mexico City that was actually painted with titanium dioxide, with a similar hope in mind that it would react away pollution in Mexico City. And so these types of things are starting to be tried at the demonstration scale. And there's a lot of hope for that as being a way for us to adapt to the changing climate. I again want to leave some time for questions that to especially the students in the audience who are pursuing degrees at Montana Tech. I want to, this is my favorite, one of my favorite quotes: "One person can make a difference, and everyone can try." And so just as a reminder, don't just find the problem, but try and find a solution as well. And with that, I'd like to thank my own students who have worked on this project over the year and welcome your questions.
Excellent. We can give you the Zoom clap. People can unmute and clap if they want.
Thank you.
Do we have questions for Des? Go ahead and unmute yourself, and you can ask Des directly.
Yeah, I also, so we had a chat in the middle. I'm sorry, I disrupted. I didn't know if my internet was unstable and Alicia was trying to tell me to slow down. But Larry Smith said the CO2 for different fossil fuel bars shows why you should always begin with 0 and not clipped. And yes, I agree. Hopefully it showed that. Yeah, close enough.
I have a question, which is
Yeah,
how much, because this importance of methane, I didn't realize was as big as it is. And I'm wondering how much methane is coming from extractive industry and how much is due to global warming and
yeah.
the tundra thawing and the methane that's coming out of the tundra.
This is a really excellent question. Thank you for that. I'm trying to find an image of the methane budget, and I'm going to reshare my screen. As I said, so I use Keynote, and it doesn't play nice with Zoom. So hopefully you can see this, and I'm going to just keep it in this view. So this is the global methane budget. This is a slightly dated one. There's a new one out from the Global Carbon Project. And they'll actually, you can find all the data you want on methane emissions. And what I want to show here is that there are lots of different sources of methane. Those are all the things on the left. The green ones are the natural fluxes. The orange ones are the anthropogenic fluxes. So things that, so there's fossil energy extraction all the way on the left, and then agriculture, that's really agriculture that wouldn't exist otherwise if we weren't cultivating it. And then the thing that Chris points out is that what about wetlands and natural emissions? So how much are we enhancing that process? And the truth is that we are enhancing that, and it is probably the case that is more responsible for the atmospheric growth in methane that I showed you, and where the observations are tracking up. So nobody really knows why that's happening, but it's postulated that is due to the acceleration of permafrost melting and wetlands giving off more methane, essentially. So you're increasing the rates of that methanogenic process. There's one more hypothesis, and that is that if you look on the right hand side of this figure, you see a big down green arrow. That's due to hydroxyl reaction in the atmosphere. And that there's a question of whether or not hydroxyl radical is going away. So there's less of it, so you don't get as much removal for some reason. But it's more a favored hypothesis, I would say, and they're still collecting data on whether or not this is actually just due to these kind of big belch events. And there's some reporting on this very recently. If you look in Siberia, there are these giant craters that are popping up. Those are due to methane explosions, essentially, that occur beneath the ground. So big pockets of methane being either released directly or exploding because they become ignitable.
Wow.
Great question.
Thanks.
So along the same lines, what's the stuff that's coming out from the fossil fuels? Is that mostly leakage, or is stuff being released, or where's the fossil fuel part coming from?
Wonderful. Yes. So there was, so it's, I would say it's both. So there's a lot of what are called fugitive emissions or off-axis emissions that are happening at an extraction site, but kind of all over the place, and they don't have very good sensing. This is a area that's really growing to try and sense and respond to those leaks. But the other term that you mentioned, I think, is from production itself. And so there's methane released during coal mining and during oil refining. There's always methane present in those processes. And so as you're moving those fluids or those solids around, they off gas methane. And so that's a part of that. Orange arrow going up into the atmosphere are those the I would say the processing emissions. So they're not necessarily fugitive emissions that nobody knows about, but process emissions. And it's not really clear what the breakdown is between those two things. So we need much better methane accounting. But one thing that is very clear is that the fugitive emissions tend to happen transiently and in heterogeneous space. And so what that means is that they occur for a little bit and then they go away and they pop up here and then over there. And that's actually very bad from an operational perspective, right? You think about yourself, playing whack-a-mole over several square kilometers, right? That's a losing game. So even if you're installing lots of sensors, you might not be able to respond to the darn leak before it stops or before you're able to go and fix it. And so there was some recent work that came out of California this year, and California really isn't the best representation for all the different types of geology that are being extracted right now, but it's at least one study that said most of the leaking is actually of this temporally transient and spatially heterogeneous nature. And so the only real hope is that a lot of those big kind of belch events, or some of them, come at compressor stations. And so you might imagine like those always having sensors on them or operational equipment that has moving parts, so you can fix that the fail part pretty quickly. But these kind of more heterogeneous belching events are tough to respond to, and this is an argument for why you would want a distributed methane conversion catalyst. So you say, okay, we give up. We don't think we can actually respond to these fugitive leaks the way that we want to. So instead, let's just take the mixed atmosphere around this gas extraction pad and try and get that methane to convert to something else. And that's a tricky problem because you can't light a flare for something that's really dilute all of a sudden and mixed into the atmosphere. So converting methane to CO2 is easy. If you have a lot of it, you just light a match. But if you don't have a lot of methane, you've got to simulate that match lighting with a catalyst, most likely. And so that's one of the things that myself and others are working on now.
Desiree, your answer made me think of the Four Corners methane leak that was in the news for a number of years, a few years ago. I don't know if you have any more recent information on that. And then my main question was, what about the oceans? How much do we really know about, leakage from near shorelines of methane and such things?
Yeah, thank you for so it's a really astute question, Larry. Yes, so the Four Corners, I don't have any updates on that, but I do think about it often. I should probably reach out and find out. So I apologize for not having an answer on that. But the ocean sources are, I think, incredibly important and remarkably understudied. I do have a history in oil development and oil extraction, and so I'll tell you what I know about oil. And this was part of the work I did as a grad student and beyond, so many years ago now. But when Deepwater Horizon happened, people were, I think, just horrified by the volume of oil that was spilling into the Gulf of Mexico. That volume of oil is actually dwarfed by what leaks out into the Gulf of Mexico naturally in the course of a year. So just to put some perspective on it for you, and with those natural oil seeps, you often get what's called methane ebullition. So there's the bubbling of methane that comes out along with the oil seep. That happens off the coast of Santa Barbara in California, and those are just places that are close to us in North America that we can see with our eyes, and really hasn't been studied very well along comprehensively along the bottom of the ocean surface. And so I think there's a lot of opportunity there, not just to get a better understanding of those methane source terms, but to also actually maybe try and capture them. Another place you might think of is lakes, right? If you've ever been out paddling on a lake that has a lot of organic matter deposition, you see little bubbles coming up. If they don't smell like rotten eggs, then it's most likely methane that's coming out of the lakes, and that's actually very poorly constrained source term to the atmosphere. But yeah, great question.
Yeah, Desiree, relating to the frac fluids, I guess, when I worked with this, well, 15 or 20 years ago, we talked a lot about containing the fluids at the drill site and controlling spills at the drill site. But what really scared us more was all these trucks full of chemicals going down the highway with guys who might not have slept in the last couple of days. And the potential for just a vehicle accident and losing the chemicals that way. So I was just curious on, away from the well site, what kind of impacts have we seen from
Yeah,
spills?
I mean, you were clairvoyant in some ways there, and the most of the impacts that we have seen are from accidents and the type of accident you described, not necessarily like a truck turnover, but a leak off of the back of a truck. And so that's where you tend to see the environmental impact showing up, not from the process itself. The process itself isn't implicitly contributing to groundwater contamination, but those other events where you've got spills elsewhere is what, at least in the eastern US, where most of the evidence comes from. There are some kind of known and allowed chemical releases. So dust control, because of the truck traffic, people are allowed to use brine in the state of Ohio, for example, to control dust. And so you see accumulation of the salts and the radioactive materials that are extracted from the earth in the extraction process showing up in on the ground surface and sometimes in drinking water and in surface waters where you might have larger disposal events. So one of the things that I've been interested in is just having a tabulation of the volumes that are moving around, and there's really no good federal structure for this. And at the state level, it's so heterogeneous that it requires me paying somebody to read through these PDF disclosures on the web, and it's just torture for them. And we also can't really compare it to anything else. So we don't know, are these spills happening at really low frequency relative to, say, oil spills? Are they happening at high frequency? Another example is like chemicals manufacturing. They have spills that are documented, but the volumes aren't really recorded very well. So it'd be great to know, is this pervasive or is it rare? And my knee jerk is that it's rare, but when you do see environmental impacts, it's often exactly sourced from what you described.
Hi, this is Kumar. So if the temperature actually increases to 2 degrees or 2.5, there is a potential that natural emissions, methane emissions might increase. And therefore, at some point of time, even if we control CO2 emissions, the methane might control the global warming. Is that something we need to be concerned with?
Yes. Can you review my latest proposals? Come on. Yeah, that's no, it is something to be concerned with. So CO2 is an acid, right? And so really the chemistry there is a lot easier than the methane capture chemistry. That doesn't mean that we're going to deploy a bunch of CO2 capture, but that science is much further along. We know how to use amine scrubbers to capture CO2. We can use that captured CO2 for more extraction processes or subterranean injection with fairly little consequence. So we don't see big impacts of those processes. It's quite well studied. The tough part is actually getting the capital to build a carbon capture tower. But with methane, we're like starting at position 0, and methane's a tiny little molecule with only van der Waals interactions. It's got it's not easy to grab. Even bacteria aren't great at it, but they've done something, and this hydroxyl radical reaction kind of gives us another lever. But we do need to get better at controlling methane, and if we could do that, then we might buy ourselves some time to transition to more renewable fuels, or to solve some of the other technological challenges that I mentioned. But we're really starting at ground zero with methane controls, and I think that people have actually been thinking about methane conversion chemistry really wrong for a very long time. So that there's a great and vast literature on converting methane to methanol at concentrated sources. So where you might have methane being stripped off of an oil distillation process, for example, or some other reactive gas like syngas or similar. In those cases, you've got lots of different methane, and you might as well just burn it and get the electricity out of it, right? So it's not very efficient. You've got a gas to liquid conversion, and then you got to collect the liquids. That's all hard. And so I think that a better strategy is actually just trying to convert ambient methane at relatively low temperatures to less potent, maybe less potent greenhouse gases or vapor methane, and let it go. Don't try and focus on capturing it for chemical utilization. Although there a lot of people are very excited about that as well, and should pursue. We need kind of all hands on deck for this problem. Good question.
Okay. Well, if we don't have any more questions for Des, those were very good questions. We are going to end the recording now, and then we will move to a small group Zoom, a separate one. So we'll log out and log back in. If you want to talk with Des a little bit more, go ahead and email me and I will send you the link. And we have her for about 19 minutes before she goes to class.
Yeah.
So thank you everybody for coming. Thank you, Des, for speaking. And email me if you want to log back in, and then the people that are going to log back in. I have to log out and then log us back in, and we'll talk to Des for a couple more minutes. So
thank you all. It's a real privilege to speak to you today.
And we hope to have you here in person sometime.
Thank you so much. Appreciate it.
Thank you. Thank you.